Good afternoon, dear participants. Uh, Welcome to the last day of this 6-day online FDP uh, on secure and intelligent system on chip, organized by Department of Electronics, Cochin University of Science and Technology, and the AICTE ATAL scheme. Today we are going to start the session with the discussion on network on chip. So as we have seen over the last few days, for an IC to become an SoC, so all ICs are not SoCs. So if an IC has to be an SoC, you need to connect multiple components together. And when we have to connect such type of such components together, you need an interconnect, and that is the significance of uh, interconnect inside the SoC. And network on chip was promising. That's why network on chip is interesting and an important part of the SoC. And in order to discuss and share or give further insights into network on chip, I think we have an expert. We have an expert in that area. Welcome, Dr. Naresh. Um, uh, it is a privilege to have you here as part of this FTP. Uh, I'll start with the formal introduction. Dr. B. Naresh Kumar Reddy. He graduated his BTech in Electronics and Communication Engineering from Sri Venkateswara University in 2010, MTech in Embedded Systems from KL University in 2012. He holds a doctoral degree in Electronics and Communication Engineering from NIT Goa, supported by Vishwesvaraya PhD scheme, Government of India. He has also spent time with Intel Technology India Private Limited, Bangalore, as the graduate intern technical. He has been with the Indian Institute of Technology, Delhi, as a postdoctoral fellow. Presently, he is an assistant professor at the Department of Electronics and Communication Engineering, National Institute of Technology, Tiruchirappalli. Dr. B. Naresh Reddy, he is currently involved in various teaching, research-related activities like network on chip, design methodologies for system on chip, VLSI system design, FPGA implementation, and embedded system. He has published over 30 SEA journals and 50 IEEE conference papers, and is a senior member of IEEE and a member of ACM. He has been recognized in the world's top 2% most influential scientists for 2022, 2023, 2024, and 2025 by Stanford University. It's very good to have you here, Dr. Naresh, and I'll hand over the session to you.
Thank you. Very good afternoon to all. First of all, thanks to Dr. Nalesh for inviting me such a deep talk. This will be purely on my domain, what I am doing the research on that network principle. Last 10 years, I am working on the SoC, MP SoC, and the NOC. Let's start talk. Is it visible?
Yes, yes.
Last 10 years, I'm working on the. I started with the SoC portion. Then after that, the MP SoC multi-process system on chip. Then later we went in the depth in network on chip. Then currently, whatever in NIT Tiruchirappalli, most of the PhD students, around the 10 PhD students and 20 MTech students are working on this domain. Is the different problem statements they have in that network concept. Yes, we are going to discuss regarding the first the introduction about the NOC, then later we'll go the research proposals about the NOC. Yeah, whatever that key takeaway. One is the NOC enables scalable high bandwidth communication for rapidly growing multi-core SoCs. Then next we'll go for the router wise. I mean to say that the packet switched architecture, it will be improving the modularity, parallelism, and system-wide data movement efficiently. Then as an academia, we are starting with the universities, the various of the topologies is there. Initially we are going to start with the mesh topology. This mesh topology offers a excellent scalability and predictable latency and simple physical implementation. Once whatever the NOC, the core and the router is completed, then we are going for the virtual channel. Those virtual channel and wormhole routing reduce the congestion, latency, and the power consumption. Then current whatever the academia 2D to 3D is expanded, then those things also we are going to discuss it. Those emerging 3D, optical, and wireless NOCs to enhance the performance and the future SOC design. Before going to the NOC, just we'll see the background of why NOC is required. Those we will discuss 10 minutes. The progression of electrons has followed a predictive path regarding the two major trends. One is the miniaturization, another one is the integration. Here, the miniaturization means all the electronic components, whatever the electronic components, get smaller over time, means whatever the resistors, the capacitors, those it will be the smaller. In 1971, first Intel is introduced 4-bit of a microprocessor. The name is 4004, 1971. That it will be the miniaturization. Once the miniaturization is there, then researchers are next to level, it will be the integration. Whatever the components, it will be the integrated in a single chip. That the Texas is introduced in 1974. The first 8-bit of a microcontroller. Normally, the Intel it is introduced in 1971. The first 4-bit 4004. The later it will be 8008, then 8080, 8085, and the 8086. Those microprocessor. Then 8-bit microprocessor, 16-bit microprocessor, 32. So they will be expanded. Then Texas Instrument is introduced the first 8-bit of microcontroller, 8051, which is a type of microcontroller with RAM and IO device integrated with the CPU on the single chip. Then once the microcontroller is there, the next level is the microcontroller is having the memory. Suppose if you want to do particular application, the microcontroller is connecting with external peripherals. If you want to connect with the 827 and keyboard display, or maybe 8255 DMA, then externally we are connecting. Rather than an external connection, for particular application, entire things it will be in a single chip. Is for that one, SoC is introduced. SoC is a system on chip. The total system is integrated in a single chip. That it means there is a single processor is working in that chip. If you have multiple of applications simultaneously need to execute. For that reason, introduce MPSoC, that multi-processor system on chip. Here, multiple of the process depends upon user, depends upon application. Choose the MPSoC platform. For suppose, if X person is having 7 applications, those 7 applications has to execute in a SoC. Assume that one application it will be 1 minute of a time execution. 1 minute of a time. Then the 7 applications, 7 minutes of a time in the SoC. If you go for MPSoC, in that the MPSoC, the user has to select how many processors is required. Depends upon your application. Suppose the X is having 7 applications, means 7 processors is required. You may choose. If you consider that the mesh analysis may be either 2/4 or maybe a 4/2, because there is a 8 process it will be there. Or you can go for 3/3. 3/3. It is M by N. Means M rows, N column. That will be the mesh. Like as a matrix, how we are doing that. The same way you can consider it. In that 7 applications, suppose assume there will be 3/3. Multi-process system on chip, if you consider that is the 9 chips, if you consider that. Any of the 7 it will be the activating. Any of the 7 it will be activating. Simultaneously will be executing. This within 1 minute, the total the 7 processes it will be activated. The 7 applications will be executed. 7 applications are executing. Then after the multi-process, in these 7 processors, want to communicate from one processor to another processor. One processor to another processor. there is a communication medium is required. Communication medium is required. Initially, the researchers are introduced. There is AMBA architecture that we are calling as advanced microcontroller bus architecture. Advanced microcontroller bus architecture. Maybe if you see the embedded systems, this AMBA architecture, it is one of the crucial concepts for the embedded system. Here is AMBA processor. Again, it will be divided into the two buses. One is simple system bus, if another one is complex system bus. If you see the textbooks, they are giving that ASB, APB, and the AHB. Means you are thinking that there is a three buses. Three buses. One is APB, advanced peripheral bus. ASB, advanced system bus. AHB, advanced high performance bus. Advanced high performance bus. These three buses as per the textbook. But as if you come to the practically, there is only the two buses, simple system bus and the complex system bus. Again, complex system bus, there will be ASB and the AHB. Now, nowhere using the advanced system bus, AHB is working currently. If you see the scenario between simple system bus and the complex system bus, if you have simple system bus means there is a single master, single slave. Single slave. The data directly it will be communicating. If you go for the complex system bus, multiple of your masters, multiple of your slaves, multiple of your masters, and multiple of your slaves. For that one, you are using the AHB, Advanced High Performance Bus. These are we given the I mean to say the advantages and the disadvantages, all the things we mentioned that the single masters and a single slave it is happened that normally we are considering single slave. Maybe if it is one or two also it is no issue. Using a simple system bus, you can use it. Then complex system bus like this AHB, advanced high performance bus. Maybe if you come to the AMBA architecture, means again the crucial component is AHB, advanced high performance bus. Why we are using the AHB in whatever the current industries is, because only one trend is it is a pipeline to transaction. Listen, pipeline to transaction. Now, if it comes to the pipeline, just 1 minute we go we give the clarification about the pipelining. Normally, if you see pipelining, pipelining is a total the process divided into the sub process. Each sub process is associated with a segment which can work independently or concurrently. Which can work independently or concurrently. Just 1 minute. I can share another PDF. It is not clear. Pipelining is total the process is divided into sub process. Each sub process associated with a segment which can work independently or concurrently. If you maybe for your purpose, I will give one real-time example. Assume that high-end laundry machine it will be. Mean to say that a high-end washing machine. High-end washing machine. Suppose in that the washing machine, there it will be washer, dryer, another one is a folder. Another one is a folder. Here is washer, dryer, folder. Washer is only washing purpose. Once the washing is completed, the next step it will be dryer. Once the dryer closed, then the third step it will be the folder. I told you that it will be a high-end washing machine. Assume that A is 20 minutes of a time. B also 20 minutes of a time. Sorry. Washer is considering as a 20 minutes of a time. Dryer also is considering the task is executing 20 minutes of a time. Folder also 20 minutes of a time. The total, if you give to the single application, means one bucket of a clothes, if you give to the washing machine, 20 minutes for the washer, then next to 20 minutes for the dryer, again 20 minutes for the folder. It will be for the single person, it will be 60 minutes of a time. Single purpose, it will be single task, it will be 60%. On single person, it will be 60 minutes of a time. If you consider four persons, there it will be 4 hours. It will be considering that 4 hours considering that. Yeah, here this example is slight variation. The washer is considering of a 30 minutes of a time. Dryer takes 40 minutes of a time. Folder takes 20 minutes of a time. If we consider a person, the name is Anne, B, Brent, T, Kathy, E, Dale. These 4 persons have washing machine. If given the one bucket of the clothes is A is having, it will be considering 30 plus 40 plus 20. Like here, A clothes 30, 40, 20. The next, once it will be completed, the B, start 30, 40, 20. Next to C, 30, 40, 20 minutes of a time, then the D. The total that time it will be 6 hours for the 4 loads. Means the 4 persons close it will be executing 6 hours. 6 hours. This is we are calling as a non-pipelining. Non-pipelining. Pipelining means process is divided into the sub process. Means washing machine is divided into washer, dryer, folder. These sub process works concurrently executing. Means so it will be, I mean to say that it will be one of it will be parallelly it will be executing. It won't depend upon another one. It won't depend upon the another one. The parallelly it will be executing. Then if you consider this case, washer A is clothes is given to the washer. Once the cloth washer is moved to the dryer, now washer is free. Then B close naked. Then once the dryer is moved to the folder, the washer is moved to the dryer, then washing C. This is the way the pipelining it will be works. If you use the pipelining, 3.5 hours it will be constrained. According the time. Earlier case there will be 6 hours. For 4 loads it will be the 6 hours. Then now if you see this how many sub processes depends upon user only. Depends upon user only. Maybe full sub process also need to consider. If you see that the 4 sub processes, this another example. Another example. Washer, dryer, folder, and storage. Storage also. Then depends upon application. Depends upon application. You can divide that how many sub processes is required. As per the pipelining, this will be in the non-pipelining. Here it will be pipelining. The main use of pipelining is execution the task or instructions within particular of a time or within clock cycles. Just to keep this fact in mind, the execution of a task within clock cycles. Execution of a task within clock cycles means within particular of a time, more number of instructions are executing. More number of instructions are executing. Then this will be pipelining is working that. Then in this pipelining, it will be contains the AHP. AHP. Then if you see that earlier it will be AHP is using that. Still in the AHP, there is some issues in there. There is some issues. Those it will be like here it will be. Assume here one more example. This it will be multi-process system on chip. That also heterogeneous. Heterogeneous. Maybe 12 process it will be there. Processor 1, processor 2, processor 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those 12 processor heterogeneous. It is not a homogeneous. Homogeneous means same size. I mean to say that the same characteristics it will be. But the heterogeneous, like as the one processor it is having that FPGA board, one processor maybe it will be the DSP processor, like that it will be the various of a processor. These 12 processors communicating, just now I mentioned if it is the 7 applications, that the 7 processors are executing. After the execution, there will be communication is required from one processor to another processor. In AHP, how it will be going that the AHP through shared bus, maybe you studied during your microprocessor. The microprocessor architecture, if you see that there is maybe 8086, there is 2 units it will be there. Bus interface unit and the execution unit. Then how it will be communicating through shared bus. Through shared bus only data it will be they are communicating from one block to another block. Here also same way through shared bus the data it will be communicating. Through shared bus the data it will be communicating. When if suppose the through shared bus the data communicated, may be data loss, may be data corrupted, data stolen, those it will be happen that way. These are drawbacks in the AMBA architecture, that is particularly in the AHP. Then again, later, researchers are introduced rather than of AMBA, NOC, that is network on chip. Network on chip. Again, this NOC is network on chip. Network on chip is communication medium among on chip of architecture, among on chip of a process, among on chip of a process. These are cores, whatever the cores it will be there. Here, this will be mesh platform. Means mesh, just now I mentioned a mesh it will be there. Whenever in the NOC, like these are cores. From one core to another core, the data is transmitted via router. So we are calling this will be whatever the square box in this router. Here, see, maybe it will be clear. Router, these are routers. Through routers only data it is communicating. Through routers only data communicating. Maybe if we consider, for example, if suppose this is a one city, then the second city, if you want to move that, like I will show that clearly how it will be NOC. Yeah, this is NOC. Normally, if you see that, maybe the core it will be large, maybe the core it will be different. This will be heterogeneous cores, different cores. In this example, I took that the 4x4 mesh NOC. In 4x4 mesh NOC, normally the NOCs contains core. Core means processor. The processor to data transmitted via network interface. Network interface. There will be wire or link. This will be a router. R means router. Through router, it will be data is communicating. Through router, it will be data communicating. Previously, the AMBA architecture is a through shared bus data it will be communicating. Here, router to router means the direct communication. From one processor to another processor, the data directly communicating. How data it will be communicating? Best example I will. Suppose ECE, Electronics and Communication Engineering, the data has to transfer from core 1 to core 16. Core 16. Data it will be transferring that. Whatever the Electronics and Communication Engineering, what entire characters converted in terms of a bits. Maybe you know that the various of a ways it will be there. Using of ASCII code, maybe ASCII code, the 7-digit code. E is having electronics, E is having 7-digit, L is having 7-digit. Like that, the total bulk bits it will be there. Maybe EBSC code it will be there. Different of the codes it will be there, converting from the character to bits. Because the ASCII code, all of them aware that. Then whatever the entire bit, assume that there will be entire things, it will comes that 1,000 bits, maybe more than 1,000. Assume that there will be 1,000 bits, it will be there. Those 1,000 bits has to transfer from processor 1 to processor 16, or core 1 to core 16. How the data it will be processing that after the conversion of a bit, that is called as a the number of bits. Again, we are converting in terms of a packets. It means it depends upon the processor. Either 256 bits, either 512 bits, either 1024 bits. Those packets, those number of bits, after collecting, it will be transferred to the network interface. Because the network interface, first to 256 bits, next to 256 bits, like that it will be receiving them. Total whatever the entire bulk of data, suppose 1,000 bits of a data, first to 256, second to 256, third to 256. The remaining bits also 256 will send. Whatever the after the 1,000, the remaining bits is assumed as a zeros. Okay. Now, network interface to router. Router won't receive the packets. It will be receive splits. Again, packet it will be divided into the splits. Either 64 bit, either 128 bits. Again, either 256 bits. Depends upon processor. Suppose assume that the 64, first to 64, next to 64, like that it will be entire data it will be. Then once if you receive the receiver, the total the 64 bit, it will be transferred to the next router, like that the data it will be moving. Just to keep in mind, here is The network on chip is a communication medium among on chip of a processor. The data is communicating from one processor to another processor directly. Data is passing one processor to another processor directly. This I consider the mesh inverse because as a beginner, these are topologies. It will be inverse topology. One is the ring topology, ring topology, octagon topology, star topology, 4 by 4 mesh, 4 by 4 torus, 4 by 4 folded torus, various of butterfly topology, then another binary topology. So many topologies are there. As academia, using the initially there will be the mesh topology as a beginner. Once if you are comfortable to doing the mesh topology, you can prefer folded torus. In industry, they are using the folded torus. Folded torus, then maybe a torus topology. Comparing to all the things, the folded torus is a better. Folded torus is better. But as a beginner, you need to learn the ring topology. A beginner, you need to learn mesh topology. Mesh topology is easy comparing to other topologies. Then now core it will be processor. Network interface is communicating from the core to router. Now we are going to discuss about the routers. NOC portion is over. Means just a brief introduction about the NOC. Now I am going to explain each and every component. How it will be working there. Means core, how it will be working. Then next network interface. Then after that the router. After that router. Here the core means the processor, how the CPU is working. The same way the core it will be working. Core it will be working. Then once the core it will be there, whatever the information, just now I mentioned one data, that is whatever the data, electronics and communication engineering. The entire things it will be converted in terms of the packets, again it converted into the flits. This router receive the flits, then that transfer the flits to the destination address. Those what entire things in terms of a packet it will be there. There is a header fleet and the type fleet it will be there and the whatever the data fleets. Then once the reaching of a router, please see the router. How the router it will be there. This will be root. In the router there will be again 5 components. One is input port. I mean to say the IO ports, input and output ports. Once the data it will be receiving, those it will be associated with the virtual channel, VC. Virtual channel. Then it will be contains the buffers. Whatever the entire data that will be filled, the 64 bits, next 64, like that it will be data storing. Then after receiving of a data, it will be transferred to the next routing logic. Third component is a routing logic. Routing logic means extract whatever the data it will be receiving, extract the header fleet. Means whatever the directions it will be, where destination only it will be showing. Then once the destination it will be received, then there will be another one is virtual channel. Switching allocator. When the switching allocator is suppose here in this example, simultaneously the data has to transfer from 2 1 means second row first column to second row third column. This is one data. Second data is first row second column to third row second column. Data has to transfer simultaneously from this place to this place. Actually, this is moving in this manner, y-axis. This is moving in the x-axis. Then during of this time, in this router, both came at same time. Both data is entered at the same time. In that time, this whatever the switching allocator will works. Just to keep this fact in our mind. Up to now, here it will be any type of a data it comes. But the switching allocator will allow only one data at a time. Because the entire bulk data it will be stored the virtual channel. But once the entire data is reaches, it extracts the destination. Based on the destination, it will check whether the route it will be free or not. If it is a free only, it will be busy. If it is a busy, the switch allocator will solve the conflict. Means here only various of routing algorithms are using that. Maybe based on the FIFO, first in, first out, or maybe based on the earliest deadline first. Here all are using the algorithms. Whatever the optimization, it will be optimization algorithm. Maybe particles form optimization and integer linear programming. Those are algorithms they are using in the switch allocator. After utilizing, after using a proof, whatever the algorithm, it has to transfer the data. Through crossbar, the data it will be transferring. Through crossbar, data it will be transferring to the output port. This is the way NOC core and the NOC router is working there. Then once if it comes to the NOC router and the NOC cores, then what type of applications are using in NOC? What type of applications are using in NOC? Just we consider that one case studies that it will be some here. Just to see that I haven't mentioned the just the router and the core entire things, it will be the single in the ring only, in this round only we are using that. Just I mentioned that MA is assume that MA is a major core. Clean means it will be free. I'm giving the clarity, I haven't explained this NOC. This it will be the T means it will be free. Whatever the dot, black dot it will be, that it will be equal. Some other applications are working on. Other application is working presently. Other application is working. This will be. Whatever the application is a failed is this. A failed application is mentioned in this symbol. This symbol. Here, these four vertices, V1, V2, V3, V4. These four vertices need to run on a NOC platform. Maybe a V1, you can use T01 position. V2, use the T02 position. That is depends upon the user, depends upon the application it will be running. Depends upon the application is running. Once if it is running, once if it is assumed that it will be completed, then we need to calculate the parameters, which is the efficient one. How we are calculating? Using the parameters. Like suppose you want to buy a bike, then what type of a parameters you are considering? First one is cost. What is the cost? Second one is mileage. How much mileage? Third one is CC. Whatever the I need to say that suppose if you want to buy higher CC, high speed if you require, then higher CC. We are buying. These just I am saying that only preliminaries. Only the three parameters. Like each and everywhere we are considering some parameters. Here also in NOC, those parameters is one is the communication energy, then the second one is the latency, third one is the throughput, latency and throughput. The first one is the communication energy. How we are calculating the communication energy? These communication energy using from theoretically I am explaining them. Usually we are using communication energy using weighted modulus distance. Maybe you are aware about the weighted modulus, how the weighted modulus distance it will be. There it will be whatever the in mesh inverse, if you consider that x-axis and y-axis, there is a two parameters. I mean some x and y for those two poles. We are calculating mod x1 minus x2 plus mod y1 minus y2. This is we are calling as a distance, communication distance. After calculating of a communication distance, multiplying with the communication rate, that it will be the communication energy. Weighted communication energy. This will be the same communication energy we are calculating for the NOCs. One is the distance, because this is a mesh NOC, right? We are considering that. Now, even the folded torus are the same way we are using that. If you go for the ring, we can't use this, whatever the communication energy example. Yes, again, I am saying that this will be useful for the mesh topology and torus topology, sorry, mesh torus, folded torus. These three topologies it is working. You can calculate with the communication distance multiplying with the communication rate. Once if it is completed, I given that one example for your understanding purpose. V0, V1, V2. These are V0 is a vertices. Maybe as a task. One task 0, task 1, task 2. From task 0 to task 1, the communication rate, normally in NOC, there is no unit for the communication energy. Just to keep this fact in your mind. If we are calculating communication energy for other things, there is a units. But in NOC network concept, there is no units because we are using a mesh because there is a two x-axis and the y-axis it will be coming. Right? There is the distance we are not calculating in the we are not at all giving the units. Then here it will be the communication. It will be the communication distance. V0 to V1. See V0 to V1. This will be 2 position. Here is 2 3 position is mapped. Suppose this is a total entire universe, it will be free. Then mapping randomly V0 V1 V2. If V0 to V1, V0 to V1, 300 multiplying with 1. 300 is multiplying with 1 is 2 2 2 3. Mod 3 minus 2 plus mod 2 minus 2. Next V0 to V2. V0 to V2. Here the 2 2 position and 2 4 position. 2 4 position means mod 4 minus 2 means 2 V0 to V2, right? Here 4 minus 2 plus 2 minus 2 means the distance is 2. 2 is multiplying with 200. See here. Previously 300 is multiplying with 1. Total it comes to the 700. Total it will be 700. Next, performance load. How it will be calculating? The performance it will be calculated in terms of latency and the throughput. One latency is communication time from the source to destination. Then next, waiting time caused by the fault. Then another one is the traffic congestion also. Waiting time caused by the congestion. These three it will be the performance parameters, sorry, latency parameters. Then coming to the throughput, just now we discussed that one example, electronics and communication engineering, that it will be converted in terms of a packets. Converted in terms of a packet. Again, packet it will be divided in terms of a plates. Yes, bulk plates we are considering. That is number of completed messages multiplying with the packet length. How much of a length? Maybe 256 or maybe a 518. Sorry, 128. Those things we are considering that. 512 or those things we are considering that. Then number of ports. How many ports it will be transferring that data? That is number of ports. Total time. How much time it will be calculated here in terms of a cycles or nanoseconds. We are calculating normally in the network concept. The cycles are seconds only we are calculating. Then these three parameters we are calculating. One is communication energy, second one is the latency, third one is a throughput. Then after that, another thing is routing topologies. Previously, we are using normal NOC topology. Once the mesh NOC, how we need to move that? Suppose the 002, 0001, 02, 03 means 1323. Suppose that it has to move from 002 to 3. How it will be moving? In this way, or maybe y-axis and x-axis means this will be XY routing algorithm. Oh, many routing algorithms are there. Researchers are included. I mean to say that depends upon application. Like I will give one more example. Suppose 4 students writing the exam classroom. If you consider the classroom is having 16 chairs, maybe 16 tables. 4 table, the first row, second table, second row, third row, fourth row. 4 rows, 4 columns. Total 16 tables are there. 4 students has to write the exam. Maybe faculty A said that all of them sit in the single row. It's 4 members. Then the faculty B said that single column. It's in the front side, all of them sit. Then the third faculty, if maybe he is very favored to the student, then he said that randomly you can sit anywhere. Fourth faculty, maybe he is a stick. He will tell that all corner position sit that way. 4 members, 4 corner position. Here, the scenario used, there is a various of a placing it will be happened. The scenario is depends upon the output. Suppose if you want to see distribution of question paper and the distribution of answer sheets, case A and case B is better. Means they are sitting in the single row and the single column. Suppose if you consider the freedom point of view, case 3 means C condition. C condition, it will be better. We are giving freedom to the students wherever you want to sit. Yeah. If you avoid malpractice, if you avoid any copying from one person to another person, the fourth case, D case, means they are sitting in the corner position, all four members. Then, like that, there is so many routing algorithms. Means then so many places it will be happen. After that, moving also from one point to another point. Then routing algorithm through how we need to move that. Maybe XY routing, east-west routing, north-south routing. Like that, those routing algorithms are there. Just to, here I mentioned that only 4 examples A, B, C, D. Then after that, the challenges, some we did that up to now. What we did that one is optimization mapping. How we are going to mapping? Just now I mentioned that these 4 students are sitting in the 16 tables. So maybe the 4 cases only I mentioned that. Maybe you can use the 5th condition. Maybe you can use adding some algorithms. So based on the algorithm, they are sitting that. Those are optimization mapping. Then another one is adaptive routing. Routing also, the data transmission from one port to another port, means one person to another person if you want to transfer. How we are sending the routing, adaptive routing. The third one is the fault tolerance. But suppose if any faults occur in the routers or if faults occur in the ports, those fault tolerance methodologies, then another 3D NOC, 3-dimensional of NOC. These 4 are challenges. Up to now, we are doing that in our lab or doing this. Already these things is completed, first 2. Then next 2 we are doing that right now. Then here the simulators all are open simulator for the MOC. That is the Naxim simulator, the regular. It will be Naxim simulator. This will be only for the mesh topology. It will be support for only mesh topology. But we are writing in the normal C, it's okay, C++ also it will working. Naxim simulator. Naxim simulator. Using of a Naxim simulator, you can calculate the delay, throughput, and power. Means the simulation point of view. Simulation point of view. How we are using the Python code, the same way it will be. You can next. Particularly router wise. If you want to do router, here Naxim is entire things core, network interface, and the router. If you want to see only the router, then the Booksim simulator. Booksim simulator. This we need to write it in the C++ only. C++. Then NOC Quick, it is similar to the Naxim simulator. It supports only 2D mesh topology. This Naxim is 2D and the 3D. Naxim is 2D and the 3D. But the NOC is only 2D technology. Like that, the so many simulators are there. We have just in this slide, I mentioned that the 5 open source simulators. Then, once the simulation is completed, we are moving to the hardware verification. For verification point of view, you can consider that the FPGAs, that it will be FPGA. You know, right? FPGA is field programmable gate array. Field programmable gate array. Why we are using the FPGAs rather than of going to fabrication means FPGA is a reconfigurable and the reprogrammable. Reconfigurable and the reprogrammable. If any mismatches happen, then you can design new one. New design you can do that. New design you can do that. Those things it will be there and this rule. Here these FPGAs, how we are using in the NOC. Those things just to 2 minutes we are going to explain. Here if you see that the FPGA which contains input and output cells, there is IO blocks. After that, there is logic blocks like whatever our. If you come to the NOC, there is a core. Next routers. Routers only it will be. These are routers. Programmable interconnect. It means one router to another router it will be communicating. This way it will be there. Means if your data want to store anything, it will be the logic blocks only. Here only the memory it will be there. Memory it will be there in this one. Then after that, whatever the routers and this will be programmable interconnect. Like FPGA is also same NOC architecture only. Then can use in the applications, various of applications are using that. Means aerospace, automotive, consumer product, and industrial point of view, some medical point of view, FPGAs are working. Just see that how FPGA is working in the NGO system. After writing of NGO simulation, then you can calculate it, whatever the parameters, the area, throughput, all that thing. Once simulation is over, you need to calculate for the chip domain, means going for the fabrication, how much of area it will be considered, then how much of a time it will be off chip memory and the on chip memory, those things. How we are writing that normal variable code only, but the connecting with the NOC directly Intel GM processor you can connect with. Those you can write the constraints, then dump that code in that NOC through FPGA to NOC. Means if you are dumping in the FPGA, means through FPGA we are communicating to the Intel processor. That will be the NOC processor. Once the NOC processor, if you implement that, you can calculate the area in terms of the lookup tables because we are connected with the FPGA, right? FPGA always the area we are calculating in terms of a lookup tables, configuration logic blocks, and flip-flops. Those it will be, we are calculating this way. Then another thing is, it can calculate the latency and the throughput. Latency and the throughput. Then once it will be completed, yeah, here is chips and FPGA have that will continue shape the future of semiconductor innovation. Means whatever the FPGA is discussing. Then just we are going to the research point of view. One topic we will consider that one of the four I mentioned that some projects. Here the first project, that is fault tolerance in network on chip. Fault tolerance, just to 10 minutes only will be taking. Now, because it will give the clear explanation of how research point of view NOC we are using the NOC we are using. There is a system level fault tolerance network on chip. Like I will give one more concept. Yeah, first we will discuss. Yeah, this NOC, like how microprocessor architecture, that it will be bus interface unit and the execution unit. Like here also, there is two units. One is the core graph unit, another one is the fault tolerance unit. Core graph unit is responsible for mapping and scheduling the core graph and NOC architecture. The fault tolerance unit is collect all the false information and providing the various of a solutions. Means various of a, if any faults occur, this will be this architecture only for the fault tolerance methodology, not a normal NOC. Just again I am saying that for this research problem only we consider this way. After that we did that one. This one of our project implemented on FPGAs and we given that measurements, whatever the parameters. Just to see that here we consider the two optimization metrics for mapping purpose. Initially I told right there it will be challenges, it will be the optimization mapping. One is the optimization mapping. For the optimization mapping, how we need to optimize. Like I said, just whatever the 4 students sitting in the 16 tables means either 4. For optimization, normally how we are considering that maybe rather than all the 4 cases, the 5th case is first 2 means 1 1 1 2. Next 2 1 2 2 means within of the first 4 only, not a row under the column. We mean that is 2 rows and 2 columns. It's 2 rows, 2 columns. The top 4 only we are considering that. If you assume that, then that this way we are considering. That will be optimization only. But here adding into the fault tolerance, assume that if any faults occur in that 4 codes, what we need to do is if any table is broken, if any chair is broken, whenever you are writing there, what we need to do that. What we are thinking that as a faculty, we are moving, we are shifting one position to another position. Here also the same way, here it will be how we did that. See here, we use 2 optimization metrics. One is NAD, node average distance. Another one is PVR, placing unmapped vertices region. Placing unmapped vertices region. These 2 node average distances, shortest average path length between among all the vertices in the networking. That all the nodes that we are calling as a node average distance. See here, whatever the V0, V1, V2, V3, rather than a random mapping or rather than a rough mapping, there it will be effective mapping. Effective mapping. Once the mapping is completed, then PVR, placing unmapped vertices region. Those PVR is unmapped codes and unmapped vertices. Here is unmapped codes always greater than unmapped vertices. Why we are considering this PVR is as per the using of a fault tolerance method. Because here is a fault tolerance unit we are using. If any faults occur during of that condition, unmapped codes are more than of unmapped vertices. Means if you use the only 4 tables in the class, if any table is placed, then where he had to where that student has to sit. Based on that condition, we consider that extra spare position. Cases belonging to 1 to n, at least one has to keep extra bed has to keep in the class. In this case, yeah, just I am saying that I am translating to that example only, whatever we did that. Then extra one we kept. Then here, first we did that, how we did that? First, initially we did this project is core mapping. Then after that, demonstrated through case study, some various of benchmarks we consider, then results, then comparative analysis for various of routing algorithms, various of routing types, how much delay is happening, throughput and the energy consumption. So all these things we consider some routing algorithm. Yeah, in this example, assume that this V0, V1, V2, V3, these are vertices or application. Here is 6 by 6 NOC. That also used NOC, used means some of them are using that, means whatever the block that it will be used busy code, means some of them is using them. Then these are failed codes. These are failed codes. Whatever the T01, T02, these are failed. These are failed. Once it will be mapping, how we are going to mapping? There is only 3, 4, 5, 6. 6 vertices required 6 tiles in the university platform. Then as per the fault, as per the second PVR, the second optimization matrix, more than up to 6 required is 7. 7. For the 7 cases, either 2 by 4 condition or either 4 by 2 condition, either 4 by 2 condition or maybe a 3 by 3 condition. 3 by 3. Yeah, optimize that the 3 by 3. At least 7 it will be has to free that. Means there is a 6 vertices, 7 it will be. Meaning, forget about these two things. Don't worry, just 7 only. Rather than after 7, we consider as a 3 by 3. We consider as a 3 by 3. Now, mapping also different. Then where he has to sit that student? Which student, either roll number wise or maybe either names wise. Like that, this will be mapping. Here the mapping is, we consider as a which vertex as a least communicating with neighboring vertices. Least communicating with the neighboring vertices. Means here neighboring vertices means either forwarding or receiving. V0 is communicating to V1, V0 is communicating to V2, V0 is communicating to the V5. Like V2 also doing this manner. See, if you consider that V0, it will be communicating with 3 vertex. V1 is 1 only, then first V1. Next to V3 is 2 only, V3. Next to V0 is 3. Even V4 also 3. Even V5 also 3. Then during of this condition, this compare, we can add the communication rate. Communication rate we need to add 1400, 200, 400. Then here 1400, 1000 and 2200. Here 200, 1200, 2000. Comparing to this one, V0. Last is V2. Last is V2. See here V2. Like that, we did the mapping. Once the mapping is completed, you can calculate the communication as per the equation I mentioned theoretically. Communication rate and the communication distance. Communication distance mod x1 minus x2. Like that, you can calculate all the things. Once it's completed, you can use the bench. Oh, yeah, here we did that. Some benchmarks also did that rather than a dynamical graphs. We consider as a static graphs. Static graph means some benchmarks it will be there based on the benchmarks. How many vertex edges 6x6 NOC platform, 10x10, 20x20. All these three conditions calculated and compared with previous papers. These two previous two works comparing that. Then once the comparison is completed, next fault, if any faults occurs, what it will be happened? There is a spare core position. You can use the spare core position inside of a 3x3 only. Means we are using extra S, right? Extra script. If any faults occur, the fault directly migrate, sorry, that whatever the working core is directly migrated to the spare core. Directly migrated to the spare core. This way it will be moving. Yeah, again, that was the spare core also we compared with we calculated with the benchmarks and compared with the previous papers. And after that, went for the FPGAs. That it will be here. Initially, we used that the Kintex 7, the high end, whatever the ultra scale we used that initially. Initially we used the 7 series. Right now, my students are using the ultra scale, either Think or Kintex ultra scale, connecting with the HPC and the LPC. That we can connect it with the FPC, Intel Xeon 5 processor, that will be MOC processor. Maybe assume that MOC is having the 8x8 cores, means max it will be the 64 cores, it will be there. You can work up to 64 cores. And some simulation is happening. After that, they implemented on those things. These works also it is. Finally, this one type of a work. Then second one is modified work, modified mesh. Maybe according to your application, you can modify that. Here we use some modification did that means why local core only connecting. Sorry, here first thing is NOC. NOC is router over onto the network interface. Every router is having 5 input output ports. 4 it will be connecting to the neighboring routers. 1 it will be connecting to the local core. Rather than after connecting local core to the 1, it will be connecting to the two routers. If you use 2 routers, some benefits and some some advantage, some disadvantage it will be there. We as per the application you may consider that. As per the application you may consider. We did this one modified 2D NOC, but so many disadvantages comparing to the advantage. Initially we thought that maybe we get benefit rather than a normal NOC, but we felt that only communication energy is better. The remaining all the things it will be disadvantage. This one work, one reason we did that. Then after that some again we given the 3D. Yeah, up to now 2 works is completed. The remaining works are doing that. One is the AI assistant, means how artificial intelligence we are integrating in this one. Next to 2D to 3D. Then another one is the wireless. Those things are currently we are doing the projects. That's thank you. If you have any queries regarding this the NOC, you can tell me, then we go for the depth about this. Whatever the concept as a research point of view, as a basic point of view, yeah, you can suggest me, or you can, if you have any queries, you may ask.
Thank you, Dr. Naresh. Any queries from the audience? Dr. Naresh, I have this one basic query. When you implement this NOCs in FPGA, how this interconnects of the FPGA means, is it means because of this the properties of the interconnects, is it going to affect the results which we get about the NOC? Means is there any correlation between that? I hope you understood the question.
Yeah. Normally, whenever if you connect with the FPGA, we get the this normal FPGA board, if you consider that, one is through we are connecting to the CPU, where whatever we are writing in Verilog code in the Vivado tool. Then once if you connect with one through high-pin into the LPC, you can connect with the NOC. In simultaneously, you can open the NARSIM simulator. Whatever the NARSIM simulator and the Vivado tool, if it is the coincide means, you can connect with the we have Intel Xeon 5 processor, that 7210 we have. That is up to 64 core only will be works. We haven't got it the high end cores. That MOC will be that platform is 64 processor. Up to 64, that also 8 by 8 MOC only. The mesh MOC only we consider that. In that the mesh MOC, you just for the task mapping, if you give that, dynamically it will be allocating into two configuration files. Configuration files it will be dynamically through HPC and the LPC can connect it.
Okay. My question is, yeah, this I understood. It's like, see, when we have the routers and the interconnects between the routers, they're
Yes.
going to be through the FPGAs interconnect, right?
Yes, exactly.
Does it impact in means add any means have you observed any impact due to because if we are, for example, implementing it as an ASIC, we are free to have any number of interconnects, right? But FPGA has a physical limitation. Have you does it have an impact, or it's, with the modern FPGA we can just ignore that?
Yes, exactly. Depends upon the FPGA, it will be considering that. Means some what happened? Those pin numbers has to verify that. Means whatever the pins, some it will be suitable, or some it will not be suitable. Once it will be suitable, it will be impact on power. That will be dynamic power. That whatever the switching power we are calculating, that will be impacted. The remaining area and everything, it will be similar only.
Okay. Okay. Got it. Yeah. Any other questions? Yeah, Dr. Naresh has shared the PPT also. I think I have already uploaded it into the drive. So if any of you have any queries about this topic, I'm sure you can contact Dr. Naresh. He will address you. I think we can wind up the session. Once again, thank you, Dr. Naresh. I'm sure that you would have been busy, especially it's a Saturday. Agreeing to be part of this FTP and sharing your insights about NOC, which is an important topic when we consider SOC, to our participants. Thank you once again. Hope to have further discussion somewhere later. Okay, thank you.
Yeah. Thank you very much. And thanks to the participants. If you have any queries, you may just to check my website. My mail ID it will be there. You may contact me.
Yeah.
Thanks.
Yeah.
Shall I leave?
Yeah. You can log out. Yeah, participants, we will stop now. The next speaker will be ready by 3:30. Please do join by 3:30. We'll have the next session. If you have any queries, you can raise now. I hope everything is okay.